We are very happy today to have Lili Shen from the University of Sichuan. We'll be talking about the categorical foundation of quantale-valued sets. Thank you very much.
All right. Thanks, Nina, for inviting me to this seminar. Today, I would like to talk something about the theory of quantale-valued sets. So, what's the idea behind the theory of quantale-valued sets? Let me start with the classical set. A classical set may be viewed as a set equipped with equality. What's the meaning? We have a set, then we have the equality relation. It can be regarded as a map from x cross x to the two-element Boolean algebra 2. So alpha xy equals 1 if and only x equals y.
I've got two casualties here, no one's helping.
Sorry, Jess. So let's continue. So we have an equality. So on this set, then it's in the 1970s, Fourman and Scott, they proposed the notion of omega set. Here, omega is a frame. Their work is based on the works of Higgs. When omega is a frame, an omega set is x equipped with a map from x cross x to omega. Here, as we have said just now, a classical set equipped with equality can be regarded as a map where the codomain is a two-element Boolean algebra. Now we replace 2 with a frame omega. The map alpha is required to satisfy the following axioms. The first one is the symmetry, alpha xy equals alpha yx. The second one is if alpha yz, the minimum of alpha yz and alpha xy less than equal to alpha xz. So what's the meaning of the omega set? In an omega set x alpha, the value alpha xy can be interpreted as the truth value of the statement that x is equal to y. So in a classical setting, between two elements in a set, there is only one relation. They are either equal or non-equal. But now we can evaluate the truth value of the statement alpha xy. So x can be equal to y, x can be not equal to y, but they have the state between the two extreme conditions. There can be the possibility that x is equal to y in some sense. So we use the elements in omega to evaluate the degree that x is equal to y. So in this case, since every element in a set is supposed to be equal to itself as long as it exists, so the value alpha xx may be understood as the level of existence of x. Let us look at some examples. The first one, when omega is just a two-element Boolean algebra, what is a two set? A two set is just an equivalence relation on a subset of x. So to be more clear, there is a subset consisting of the elements that satisfy alpha xx equals 1. And in this subset, alpha is just an equivalence relation on this subset. So in this subset, the elements are supposed to exist. In particular, X alpha reduces to a classical set if it satisfies two conditions. The first one is that X is separated. It means that alpha xy equals 1 if and only if X equals Y. And the second one is global. it means that alpha xx equals 1 for all x. Here I mean that the classical set is just a separated and a global two set. So this is the simplest case. And in the paper of Fourman and Scott, they propose a non-trivial example as the following. When we have a topological space X, we can consider the set of partially defined continuous functions on open subsets of X. So it means that here we denote it by PCX. PC means partially defined continuous maps. So we consider an open subset of X, which is the domain of F. So we denote it by DF. All the continuous maps from DF to R consists of this set PCX. And for functions in PCX, we can consider the following equality, which is defined by alpha fg is the interior of the which is the interior of the elements which makes f and g equal. So in this sense, PCX and alpha consists of an OX set. Here OX is a frame of open subsets of X. Then Fourman and Scott, they consider the category of omega sets. So in order to define the category of omega sets, we have to define what's the morphism between omega sets. The definition of a morphism between omega sets is as following, and it seems quite complicated. So I will not look into the details now. Later, I will explain what's the categorical meaning behind this morphism. So the category of omega sets and their morphisms constitute a category we denoted by omega set. Omega set is a very interesting category. In fact, we can connect omega set to sheaves on omega. Because omega is a frame, or it can be also said to be a locale, we can define sheaf on a locale. So starting from an omega set, we may construct a sheaf on omega, which is given by, because when we want to define the sheaf, when we want to define a sheaf, we have to tell you what's the image of f acting on each u in omega. So fu is precisely the elements of x whose extent of extents is u. And conversely, starting from a sheaf f on omega, we can construct an omega set where in the omega set x is precisely the union of all fu. And for each element in fu, the extent of existence is precisely u. And alpha xy is the join of all the elements less than or equal to u, the minimum of u and v, which the section of x and y on w are equal. So under this correspondence, Fourman and Scott proved that omega set is equivalent to the category of sheaves on omega. This is one of the main results in this paper. So as a consequence, we know that omega set is a topos because sheaves on omega constitute a topos. In this sense, the topos theory can be regarded as the categorical foundation for both classical sets and omega sets. So this is the background of this talk, the theory of omega sets. We have seen that what's the definition of omega set, and they constitute a category that is equivalent to the category of sheaves and omega. And our purpose is to investigate the theory of quantale-valued set, which means that we want to generalize a frame omega to a quantile. We want to discuss what's the meaning of quantale-valued set. So what is a quantile? For simplicity, we consider a commutative and divisible quantile. Commutative means that the monoid operation on this Q is commutative, and divisible means that it satisfies a certain divisibility condition. In fact, the theory of quantale-valued set can be defined on an arbitrary unital quantile. Here in this talk, we only deal with commutative and divisible quantile just for simplicity, because for an arbitrary quantile, the definition of quantale-valued set is more complicated. So here, we just talk about commutative and divisible quantile. So Q and 1 becomes a commutative monoid. Q is a complete lattice. And the monoid operation on Q preserves suprema. Since it preserves suprema, it induces a right joint. The right joint is called the implication in Q. So here the formula in blue, P and Q less than equal to R if and only if P is less than Q, the implication of Q and R. So, and the last condition in the bottom of this page is the divisibility condition. Whenever U is less than or equal to Q, we have U equals to Q and Q implying U. Since every frame is a commutative and idempotent quantile, so frame is a special case of commutative and divisible quantile. In fact, the difference between a frame and a quantile is the idempotence. In a frame, the monoid operation is just the minimal. So minimal is idempotent, but in a quantile, the monoid operation we denote it by the and symbol. The symbol and is usually not idempotent. So it's natural to ask what is a quantale-valued set. In fact, this theory, the theory of quantale-valued sets, has been studied for many years. I think the most notable approach is the way taken by Höhle and his collaborators, mostly Höhle and Ulrich Höhle and Thomas Kubiak. They proposed the notion of Q set. So let's see what's the meaning of Q set. Let me elaborate this notion in the way of enriched category theory. First, we see that every frame omega induces a quantaloid d omega. So what is a quantaloid? Later I will explain this notion in details. Every frame omega induces a quantaloid d omega. The objects of d omega are the elements of omega. And for PQ in omega, d omega PQ consists of the elements in omega that is less than or equal to both P and Q. And the composition is just given by the composition of E and D, just given by the minimum of E and D. And the identity morphism on Q is given by Q itself. This construction can be traced back to R.C. Waters in a paper in 1981. In this paper, sheaves and Cauchy-complete categories. So what is a quantaloid? A quantaloid is just a category Q whose home sets are complete lattices. So a quantaloid is a category enriched in the category soup of complete lattices and super-reserving maps. So we require that every home set is a complete lattice, and we require that the composition of morphisms preserve suprema. So since it preserves suprema, it's like the quantile. It can induce right joins. The right joins are also called implication in Q. So because the composition of morphisms has two directions, so it can induce two right joins. They are respectively called the left implication and the right implication. So the left implication, we use an arrow from the up right corner to the left down corner, and the right implication is denoted by an arrow from the left up corner to the down right corner. When we have a small quantaloid Q, which means that the set of objects of Q constitute a set, we use Q0 to denote that set. When we have a small quantaloid, we can define Q0 type set. It's simply a map from a set X to Q0, so that every element of X has a type. The type, we denote by the symbol of the absolute value. So when we have a small quantaloid, we may consider a category enriched in Q. It's a category enriched in a bicategory, not a symmetric monoid closed category. It's a bicategory. We can consider category enriched in Q. What is a Q category? A Q category consists of a Q0 type set X and a family of Q arrows alpha XY from the type of X to the type of Y, such that alpha XX is greater than or equal to the identity arrow on the type of X. And alpha YZ, the composition of alpha YZ and alpha XY is less than or equal to alpha XZ. This is the definition of Q category. Then, when we have Q categories, we can define Q functors. A Q functor between two Q categories is a type preserving map, and such that type preserving means that the type of X is always equal to the type of Fx. Then alpha X prime is less than or equal to beta Fx prime. The category of Q categories and Q functors is denoted by Qcat. And more importantly, we are interested in another morphism between Q categories. It's called Q distributor. The Q distributor can be considered as the Q variant of the notion of distributor. A Q distributor between two Q categories, it assigns a morphism between the type of X and the type of Y for each pair XY, such that the following inequality holds, which means that you can consider it as if phi xy, we have the phi xy, and it's compatible. It must be compatible with the Q category structure on both X and Y. So we have a category QDist. Its objects are Q categories and its morphisms are Q distributors. This is a large quantaloid. And the composition is given by the join of phi and psi to Q distributors. It's a join of all pairs psi yz and phi xy, ranging from h, y in y. And the identity Q distributor on X alpha is just given by the Q category structure alpha on this Q category. So just now I mentioned that Q dist is again a quantaloid. So in particular, it is by category. And we can define adjunctions in Q dist in a canonical way, which means that two Q distributors, phi and psi, form an adjunction if psi, the composition of psi and phi is greater than or equal to alpha, and the composition of phi and psi is less than or equal to beta. And phi is called the left joint, and psi is called the right joint. This is the standard definition in category theory. So now we can have a look at the d omega category. Just now I mentioned that every frame omega induces a quantaloid d omega. In the quantaloid d omega, the objects are the elements of omega, and the morphisms between P and Q are the elements less than or equal to P and Q. So translating the definition of quantaloid enriched category to the special case of d omega category. So we can see that a d omega category consists of a map X, a type map from X to omega, because omega is precisely the set of objects of d omega. So the type map is from X to omega itself. And we have a map alpha from X cross X to omega, such that alpha xy is less than or equal to the type of X minimum the type of Y, which is the type of Y. Because what's the meaning of the first condition? It means that alpha xy must be a morphism in d omega from the type of X to the type of Y. And the second condition, alpha xx greater than equal to the type of X, is the first condition of quantaloid enriched category. It's a reflexivity. And the third condition is the transitivity of d omega category, because composition in d omega is precisely the minimal operation. So alpha yz, which is alpha xy less than or equal to alpha xz. So let's combine the first condition and the second condition. When you look at the first and the second condition, you can see that it forces the type of X to be alpha xx. So a d omega category consists of a set X and a map alpha, because the type map is precisely incorporated in the structure map alpha. So the first and the second condition becomes alpha xy less than or equal to alpha xx, which is alpha yy, and alpha yz, which is alpha xy less than or equal to alpha xz. And a d omega category is symmetric if alpha xy equals alpha yx. So we can see that an omega set is precisely a symmetric d omega category. And what's the category of omega sets? The category omega set is precisely the category of symmetric d omega categories and left joint d omega distributors. Remember just now I said that the conditions for morphism between omega sets looks very complicated. And now we can see that it's nothing but left joint d omega distributors. So the category of omega sets is precisely the category of symmetric d omega categories and left joint d omega distributors. Now we have seen that what's the categorical meaning of the category of omega set. So translating from omega sets to quantale-valued sets, we only need to do one thing, that is replace omega with a quantile q. In fact, from a quantile q, we can also define a quantaloid, we denoted by dq. So what's a quantaloid dq? Objects of dq are elements of pq in q. Here, we require that the q is commutative and divisible. If we don't have this condition, the definition can be more complicated, especially for the first one, objects of dq. When q is commutative and divisible, we can put all the elements of q to be the objects of dq. But when q is not divisible, we can only select the so-called divisible elements of q to be the objects of dq. So that's a difference. And for elements of pq of q, we can define the morphisms between p and q to be elements of q that is less than or equal to both p and q. And the composition of E and D is E and Q implying D. And the identity morphism on Q is also Q itself. So we can see a bit more about the quantaloid DQ here. In fact, the construction of DQ is a very general structure in category theory. From every category C, we can define a category DC. From every category C, you can define a category DC in the same way. So it's in fact a quotient category of the category of arrow category of C. From every category C, we can define a category DC is a quotient category of the arrow category of C. So if we apply this general construction to a frame omega or to a quantile q, we have the quantaloid dq or d omega. So this is a very standard construction. Now, what is a dq category? Again, we translate the definition of a general quantaloid enriched category to the special case of dq category. A dq category consists of a set X and a type map from X to Q and a structure map alpha from X cross X to Q. So we also have three conditions. The first one, alpha xy is less than or equal to the type of X, which is the type of Y. This means that alpha xy must be a morphism from the type of X to the type of Y. And the second is the reflexivity condition, alpha x greater than or equal to the type of X. And the third one is the transitivity, because the composition in DQ is defined in this way. So the transitivity condition becomes like this. And similar to the case of d omega, we can also see that the first two conditions, the first two inequalities would force the type of X to be alpha XX. So the type map is also absorbed by the structure map. Hence, the DQ category consists of a set X and the structure map such that alpha XY is less than or equal to alpha XX, which is alpha YY. And the second one is the transitivity condition. And similarly, a DQ category is symmetric if alpha xy is equal to alpha yx. So we can define a Q set precisely to be a symmetric DQ category. A Q set is precisely a symmetric DQ category. It's just the in fact, in the definition, we only do one thing, that is changing the frame omega to a quantile. A symmetric DQ category is precisely a Q set. So in elementary words, a Q set consists of a set X equipped with a map such that we have the following three conditions: alpha xy less than or equal to alpha xx, which is alpha yy, and the symmetry condition and the transitivity condition. Here, we also understand the value alpha xy as the truth value of the statement x is equal to y. Since every element is supposed to be equal to itself as long as it exists, so the value alpha xx is considered as the extent of existence of x. So the three conditions of a Q set can be interpreted as follows. Every entity is more equal to itself than any other one. And if x is equal to y, then y is equal to x. If y is equal to z, and there exists y that x is equal to x, then x is equal to z. So now the next question would be, why should we consider Q sets when we already have omega sets? In fact, as I mentioned just now, the most important distinction between a frame omega and a quantile Q is that a frame is always idempotent. The monoid operation on a frame is idempotent, but in general, a quantile is not idempotent. The monoid operation on a quantile is not idempotent. So the idempotency is essential for quantile. So we can have many more examples than frame value sets. I think the most important one is when Q is defined to be the Lovell quantile, whose underlying set is the extended half-real line from 0 to infinity. And the order on this interval is taken to be the reverse order, that is the greater than or equal to the order. And the monoid operation on this interval is just the plus, and the unit for plus is just 0. So what are the 0 infinity sets? If we take 0 infinity to be the Lovell quantile, so what are 0 infinity sets? They are precisely symmetric partial matrix spaces. That is, a set X equipped with a distance map such that the following three conditions are fulfilled. The first one means that the distance between x and y is greater than or equal to alpha xx and alpha yy. So the difference between partial matrix space and matrix space is that the distance between an element of itself can be non-zero. So alpha xx may not be 0. So we have the first condition requiring that alpha xy must be greater than or equal to alpha xx and also greater than or equal to alpha yy. So the distance between two different elements is always greater than or equal to the distance of this element between this element and itself. And the second condition is the symmetry of the distance. And the third condition is the triangular inequality in partial matrix space. The distance between xz is less than or equal to the distance between y and z plus the distance between x and y. And here we must minus the distance of y between y and itself. So when you look at this example, why should we investigate partial matrix space, there is, for example, if you consider X to be a set of different cities, we have a lot of cities, and you consider the transport fee to transport goods from a city to another city. So, and if you don't go to any city, you just stay in the same city, you will be still charged a storage fee. So alpha xx is not zero because you may be charged a storage fee for staying in the city. And the triangular inequality, you can see that alpha xz is less than or equal to alpha yz minus alpha yy plus alpha xy. Why should we minus alpha yy? Because the storage fee in y is charged twice, so you have to minus 1 to. So you can consider partial matrix space in this way. And in the special case that alpha xx is actually 0, as in the classical setting, we reduce to the classical matrix space. Here's an example. If you consider a set of closed intervals contained in 0, infinity, then we can define a partial matrix on closed subintervals of 0, infinity. Given two closed intervals AB and CD, their distance can be defined by the maximum B and D minus the minimum A and C. This is a symmetric partial matrix space. So the Lovell quanta is just is a very famous construction in category theory, as I think we all know it. And the second one, partial matrix space, is taken from the paper Partial Matrix Topology from Mike Hughes in 1994. So just now we have mentioned that when Q is a frame, we already say that omega set, the category of symmetric d omega categories as left joint d omega distributors, omega set is a topos. So it's natural to ask, if we change omega to Q, is the category Q set of symmetric DQ categories and the left joint DQ distributors, is it a topos? That's a natural question. Almost 14 years ago, in a paper, in the footnote, in the paper I mentioned in the footnote, pre-order says valuing a geomonoid. It was conjectured that for commutative and divisible contact Q, the category Q set is a topos if and only if Q is a frame. That is to say, if you want Q set to be a topos, the monoid operation on Q must be idempotent. If it is not idempotent, then Q set cannot be a topos. And we prove it in the last year. So let me explain this a bit more. And just now I mentioned that because for frame value sets, when Q is a frame, for every frame omega set is a topos. So the topos theory can be regarded as a categorical foundation for omega sets. But since in general Q set cannot be a topos, so the topos theory is unlikely to serve as a categorical foundation of Q sets. So why? Let me sketch the proof to illustrate the idea behind this. First, when we deal with the category Q set, in fact, because the morphism in Q set is quite complicated, because the morphism in the category Q set is a left joint DQ distributor, and the distributor is much more difficult, is much more complicated than functor. So it's not easy to deal with distributors. So the first step is to switch the category under consideration to another category whose morphisms are functors. In fact, the category Q set is equivalent to the fork subcategory of the category of DQ categories and DQ functors, whose objects are separated and Cauchy-complete Q sets. And in a topos, we know the following two propositions from the topos theory. The first one is that every monical arrow in a topos is an equalizer, and in a topos, the sub-objects of an object X is a lattice, where the intersection of sub-objects is given by a pullback, and the union of two sub-objects is given by a push-out. So in a topos, we know that every monical arrow is an equalizer, and the intersection and the union of sub-objects can be defined by pullback and push-out. This is our main tool to prove our theorem. So we define another order on the quantile Q. For every PQ, we define a new subset CQ. What's the meaning of CQ? You can see that we take elements below Q, which satisfy P and Q, implying P equals P. So we have the square less than or equal to P, square less than or equal to Q, if and only if P is in CQ. This condition is somewhat like the divisibility condition, but it's different. And we can prove that, we prove by contradiction. We can prove that whenever the category of Cauchy-complete DQ sets is a topos, then for each Q, every sub-object of CQ in this category is of the following form, which is CP and which it means that the Q set structure in CP is precisely given by the minimal operation. This is what we can prove. Then we can show that if the category of Cauchy-complete Q sets is a topos, then the first minimal, the square minimal, what's the meaning? It's calculated in the new order we defined just now. It's calculated in this order, square less than or equal to, just now we defined this order. If this category is a topos, then we can show that in the new order, the minimum of P and Q is equal to the original minimum of P and Q in the original order. So how do we prove this lemma? This lemma is proved by just exploring the intersections and the unions in the lattice. If it is a topos, then the intersection of the union must be given by the pullback and the push out. So we can calculate it step by step, and we can prove this. Lemma. And with this lemma, we can prove our theorem, because in this case, we can show that every element Q is idempotent. That is, Q and Q equals Q. So Q must be a frame. So this is the sketch of this proof. And as a special case, we consider the following quanta. This quanta, the underlying set of this quanta is the unit interval from 0 to 1. Unit interval, the real numbers between 0 and 1. And the monoid operation on this set is the so-called continuous t-norm. What's the meaning of continuous t-norm? A t-norm is a binary operation on the unit interval, and the continuity condition means that it is continuous with respect to the usual topology on the interval 0 and 1, 0 to 1. So we may consider the unit interval from 0 to 1 and the monoid operation on this interval, and we take 1 to be the unit of this operation. Then we have the definition of continuous t-norm. In fact, a continuous t-norm is precisely a divisible quanta on the unit interval. So as a corollary, let star be a continuous t-norm on the unit interval. The category of 0, 1 sets is a topos if and only if star is the minimal t-norm on this interval, because a continuous t-norm becomes a frame if and only if the operation star is precisely the minimal operation. So since we already know that in general this is not a topos, we may still wish to ask, does it satisfy some other properties, topos-like properties of, because in a topos we have different requirements for it to be a topos, such as subobject classifier and the Cartesian closed. Well, just now we proved this theorem, we proved this result by exploring subobjects in this category. And we may also wonder whether this category can be Cartesian closed. So the second result I would like to introduce today is the Cartesian closeness of the category of Q set. But for a general Q, this is very difficult. As a first step, we deal with the special case of real value sets, which means that the quanta Q under consideration is taken from a continuous t-norm on the unit interval from 0 to 1. And our result is that the category of 0, 1 sets is Cartesian closed if and only if it's the same condition, star is the minimal t-norm on 0, 1. So how do we prove this result? The method is also in the same way, because as I mentioned just now, left joint distributors is too difficult to be tackled with because these conditions are too complicated. So we also switch from the category of distributors to the category of functors. But to consider the category of functors, we have to restrict the objects to Cauchy complete ones. Then we consider the category of separated Cauchy complete 0, 1 sets and D01 functors. And these two categories, they are equivalent. So we can consider the second category instead. And our key lemma is the following one. For real numbers PQ in the unit interval, the following statements are equivalent. Because consider the one element 0, 1 sets P and Q. A morphism phi is a morphism between one element 0, 1 sets if and only if either P equals Q or else P less than Q and P is idempotent. So in this case, it necessarily holds that phi PQ must be Q, must be P. So a morphism between one element 0, 1 set when it exists will be denoted by overline P because it must be P. And our strategy is that if this category is a topos, if this category is Cartesian closed, then we have the exponential of z and y over z. So what's the exponential look like? We can translate it between the natural bijections. So in this way, we can show that the exponential must behave in this way. So if we have this exponential, then every map f in this exponential will be mapped to this this set. So we can after some routine calculations, we can see that if the exponential exists in this category, then the structure on this exponential must be in the form of this one. However, we can show that if star is not the minimal t-norm on the unit interval, there will exist a non-trivial closed interval inside the unit interval. And in this way, we can construct a special 0, 1 set y and a special 0, 1 set z such that the exponential equipped with the structure here in the formula 1 cannot be a 0, 1 set. So I mean that what's a way of proving this? We show that the exponential, when it exists, it must be in the form of formula 1. But we construct a special example such that if star is not the minimal t-norm, then we can construct a special y and a special z such that the exponential equipped with the formula 1 structure cannot be a 0, 1 set, so it cannot be Cartesian closed. So that's a proof. So these are the main results that I would like to introduce about the quantale-valued sets. So as a summary, why will we care about this? In fact, we want to find the categorical foundation of the theory of quantale-valued sets. What's the meaning of categorical foundation? The meaning is that for omega sets, we know that for every frame omega set is a topos. So topos can be considered as the categorical foundation. But for quantale-valued sets, for general quantile Q, in general, Q set is not a topos. So when we want to discuss the category of Q sets, what should it be? It can be a topos. So what can it be? That's something that we are working for many years. We want to search for a categorical framework for Q sets. And in particular, for the Cartesian closeness of Q set, just now we derived this result for a special Q, which is the unit interval equipped with the continuous T norm. But what's the behavior for general Q? We still don't know. That's also our concern in the future. So thank you.
Thank you very much, Lily, for the nice talk. Are there any questions? Okay, if not, I have a few actually. So the first one is there are intermediate notions of, or weaker notions of Cartesian closure. For example, restriction Cartesian closure. Do you think that if you have weaker conditions of on your quantile than being a frame, so this would be a Posetto Cartesian closed category, but for example, if it's a Posetto restriction closed category, you can obtain a similar result on Q sets?
Yes, in fact, because we want to know whether Q set is Cartesian closed, but to deal with the general Q is very difficult. So we only derive this result in a special case, which is Q when Q is the unit interval.
But what's the main
And
difficulty in dealing with general Q sets?
because in the proof, we must I think in the proof of this lemma, we have to require that the order on 0, 1 is a linear order. If it is not a linear order as in a general Q, we cannot prove this lemma.
I see. Because I'm familiar with a different result by, I'm sure you know, Isarstub, where he
Yeah,
studies where Kant Q is Cartesian closed for a general
yeah.
Q.
Yeah, I also noticed their paper recently.
But they
But
don't follow the same proof path as yours.
I think we are dealing with different categories because our
Yes,
category,
no, I agree. But they
yeah,
don't need to assume a linear order to prove it.
yes.
Okay. And so my last question is not necessarily for the question of Cartesian closure, but in general, have you considered Q sets when Q is not a quantile, but you work in the categorical case where you have cosmos, basically, so by complete monoidal closed category?
As I mentioned just now, because when defining Q set, the key construction is the category DQ. Because
Yes, and
we
this can be
define
done
a
in
Q set
general,
to be a symmetric DQ category. Yes, because this construction works for every category C. You can
right?
take a category C and consider the error category and consider a quotient category. Then you can also define a category DC. And I think if this C satisfies certain conditions, you can construct the so-called symmetric DC category and call it the, for example, C set. I think you can do that, but it might be very, very complicated
I
in the
see.
general case.
Okay, thank you. I see Soichiro has a question.
Yes, thank you for the nice talk. So I have a question on this construction of the controlled DQ.
Yeah.
So is it possible to give a characterization of this construction by some universal property?
Yeah. And because in a general case, when C is a general category, I think this construction was constructed by Marco Grandis
Okay,
maybe 20 years ago. They were already published in JPAA 20 years ago
okay.
for this construction. I mentioned them once in our paper, True Connections. I think you know that paper.
Yes. Yeah. Okay. Yeah, so I'm trying to understand this construction. What is it possible to view this DQ as some sort of completion of Q? Or
Yes. I
and it,
think
yes.
I think Grant is calling it the AP mono completion of a category.
Okay. Oh, thank you. Then I will take a look at Randy's paper. Thank you.
Okay, thank you very much. Are there any other questions? Well, if not, thank you very much again, Lily, for the very nice talk.
Thank you.